Hi guys, welcome. I did get an email from the facilities and they said that the work order is complete. So I haven't heard it in a couple of days and I don't know if that class just gave up and quit or if it's just that we're not hearing them anymore, but it's not fixed? Shoot. Well, all right. Let's look at some announcements just to get started. So you've just finished an assignment and the PDF of the solution should be available now. I set that to auto-release right at 3:30 p.m. So you should see it if you want to. I only did 2 iterations in my solutions. My hand was getting tired. So I think that it converges after 2 though. All right, looking a little bit further into the future, our first exam of the semester, I just wanted to make the point that there's going to be Excel questions on that exam. And when I was grading the homework where you had the 3 reservoirs homework, I noticed that some students started from scratch on that and some people adapted the template that I had provided previously. And that's fine, but on the exam, you're not going to adapt a template that's been previously provided. You'll be using your brain and your past experience, and I will allow you to bring in a sheet of notes. And so if you want to provide column headers or instructions to yourself, then that'll be fine for the exam, but it'll be with a blank workbook that you begin any Excel question on the exam. All right. Yes? I'm going to give you that same equation packet that I distributed before. I think I posted it online, right? I didn't print out a copy of it, though. So it's several pages long. I'll give you that. In addition to that, you can also bring in 1 page of your own notes, hints, and so on. Other questions? All right. Well, we've talked about calculators in the past, and I've been thinking about it a little bit, like why I like the HP 50, and I wanted to make one point that you're going to be in engineering for a while, at least to the end of the semester, right? And maybe even further. You're probably starting a career that could last 50 years. And so investing in a good calculator is not, not too crazy. I know that the Casio calculator is only $15 and this one's $85, but if you amortize that over a 50-year career, then the difference in cost is marginal. And there are some things this calculator can do that the Casio maybe can do, but not as neatly, or sometimes it's just things that it can't do at all. And so I made one brief video just to give you an idea of, I got an emulator. I got an emulator just to show you the Colebrook equation, and I shouldn't have started there because the Colebrook equation is not like the sexiest contrast of Casio versus HP, but I mean, it at least gives you an idea of how you can enter equations graphically in the HP, which is one of the things I appreciated about it. All right, so let me show you that little video. I just made it this afternoon. Okay.
In this demo, I'm going to show how to use the HP 50G calculator to solve the Colebrook equation. Now, the Colebrook equation can sometimes be tricky to solve. What we're looking for is to try and find an f value, and you'll notice that this is an explicit equation where f is found on both sides of the equation. And so isolating it algebraically isn't possible, and so we have to solve the problem numerically with iterative guesses of f to try and get the 2 sides of the equation to equal each other. So these are just some flow conditions that I took from a previous example where we have a pipe with a diameter of 136 millimeters. It's galvanized iron, which tells us the K sub S value, which is the equivalent sand roughness for the material. And the flow conditions, meaning the velocity, the diameter, and the kinematic viscosity, are yielding a Reynolds number of 1.8 million. So I'm going to, first of all, enter the calculator's numerical solver by pushing this orange 7. You'll notice that here, in addition to the number that's on the key, there's white and orange instructions that are associated with each of the keys. So I've just done the orange, which is this right arrow, and you can notice up here at the top there's also a right arrow to tell you that that's active, so that the next button I push will enter the numerical solver. It has a lot of different possibilities: differential equations, polynomials, linear systems, finance, and so on. I'm just going to do the simple equation solver. So I can either do OK by pushing this button beneath OK, or enter, since I'm on the line that I want to be on. So I'm going to enter the equation solver. Now, I've been previously double checking everything to make sure, so these values may be blank the first time you solve it, but what you do is you enter the equation writer. You can type in the equation in kind of this clumsy one line, really confusing, awful to try to use kind of way, or in the equation writer, see here in orange, EQW. So I'm going to do orange, EQW. Now I can construct the equation in a way that's visually exactly the same as I see it on the screen here. So 1 divided by the square root of f. I'm pushing the alpha button, which is yellow, to get the f that's over here on this key, is equal to, orange, equal 2, and it's minus 2, so I need to put the minus sign on there with the plus minus. That toggles the value, and I want it to be minus. Log k sub s, so I'm going to call that just the variable k, divided by 3.7d plus 2.51 divided by r is what I'm going to call the Reynolds number, square root of f. Okay. So the equation is entered. I can say enter, and then I'm going to put in the values that I know are true. So 0.15 is the k value, the diameter 136. Now these are previously in the memory from the last time I tried the example. So I don't necessarily have to type it in because it's already there, but just to show you, enter in those values, and then you click over here on solve when you go to the field that you want to know, solve. So if I changed it from this galvanized iron to another pipe material, let's say that I change it over to cast iron, which would maybe have 0.26, I can adjust that and calculate the new friction factor by solving. And now these numbers, by the way, you'll notice it's actually times 10 to the minus 2. And it also, if I go to enter, it has the values in the stack. And so this is the first value that I solved for, 0.0203. And then the second one, when I change the k sub s, is loaded here, the second solution. I can go back into the numerical solver again, and all that information will still be there, so that if I wanted to play around with things even further, if I wanted to change for a new pipe diameter, let's say I'm going to have, oh, that seems a little bit high, 500 millimeter pipe diameter, and then solve for the new F value under those circumstances, then it can just adapt as many times as I want to, and it keeps solving for the updated F value. And so it's pretty handy. I think the main advantage of the HP calculator in this sense is that equation writer, because it allows you to construct the equation in a really graphical way.
All right, thank you for indulging me. The propaganda will continue periodically. If any of you end up buying this HP 50 calculator, I can give, you know, like maybe a 20-minute demo of some of the really, like the most unique advantages it has, some of its like things with matrices and units conversion and so on. So, yeah, you can save the equation as a variable, and you couldn't take that calculator into the FE exam. It's just simply too powerful, but you can bring it into this exam. So anything you want to program into that calculator, do it. It's fair game, anything you want. So anyways, all right, so today is kind of a fun day because we get to use Excel for the Hardy Cross method. we're going to be automating the calculations I tried to cram onto the whiteboard last time. Now, the key to all of this is beginning with a guess of our flow directions and flow rates. Let me hand out a copy of the example that we're going to be working today, because your first task is to come up with a guess of the flow rates that satisfies continuity. And of course that means that for every junction the flow in should equal the flow out. This is where we're going to assign those guesses of flow rate through each pipe. And a better guess is going to mean that it converges faster, but as long as it honors continuity, it'll converge. And so it doesn't have to be perfect. Okay, so I've just given you the sketch here. And so what I'd like you to do on the sketch is, let's say, for example, this junction A, where we know that there's 1 cubic meter per second going in. There has to be 1 cubic meter per second going out. So split that flow between pipe AF and AB. On your paper with a pencil probably, because inevitably you might want to make some changes. Draw an arrow and then indicating the flow direction, and then the amount. And do that same thing at every junction. So when you get to junction B, based on the arrows that you already have defined, figure out what direction and amount you're going to have through BC, and so on. Just from junction to junction, assign the directions, and then consult with your classmates. Now, you can have a different value as the person sitting next to you, but what should be true among everyone is that at every junction, in should equal out. All right, so once you've defined your flow balance, then open up a fresh workbook in Excel and put these new column headings in. There are a couple of new ones that we didn't have on the example last time in class, simply because we were a little bit cramped for space. We're going to keep track of the percent change of the flow rate from the initial flow rate to the corrected flow rate, just as an indication of convergence. Remember that when it's changing less than about 1% is when we feel comfortable that the solution has converged. And so you can put all those column headings in. Okay, so once you've got the headers in, then you're just going to start filling in the data that you have from the drawing into the spreadsheet. So you're going to have to identify, remember, how many loops there are, the clockwise direction. You're going to have to decide if flows are positive versus negative, depending on whether they're clockwise or counterclockwise. There's going to be the issue of some of the pipes will be in both loops. Pipe EF and CE, both of those pipes are common between the two loops. And so what's the thing that we have to remember in those cases? Yeah, so When you're looking at it from the perspective of the top loop, for example, the flow direction may be from E to F. Well, that would be considered positive, but in the perspective of the lower loop, that would be considered negative. And so be careful on your signs. And then the other commonly forgotten important thing is always use the most recently updated value of F and Q. And so you're going to start off with the flow rates in the first loop, first iteration. Just use your flow rates that you wrote down on the paper, that continuity developed flow rates. But in the first iteration, second loop, you have a better guess for EF and CE. So always use the best, most recent guess that you have for flow rate. That's nice. It says on the handout the epsilon for all of them is 0.3 millimeters, right? Okay, just to address the workflow, once you start getting the pipe parameters in, we don't know any velocity to begin with, and so our best guess initially is fully turbulent flow, which means that the Jane equation is going to simplify to the Reynolds number term canceling out, and it's just the K sub s divided by d that does it for us on that first iteration. But for subsequent iterations, we will have velocities and Reynolds numbers and so on, and so we can use the most recent version of those that are available. Over here, no, it should be the absolute value of the velocity. All right, let me give you one tip that is a little bit strange compared to how we usually do things. Like in Excel, we like to type in equations one time and then drag it down so that you don't have to type it in a bunch of times, right? We're not going to really be able to do that for this one. Here for the corrected Q, because of the way that we're going to copy and paste in subsequent iterations, we don't want to be anchoring to cell references here. And so the best way that I've thought of to do it is just your first iteration, you have to type this equation in as many times as you need it. And that way, on subsequent iterations, when you copy and paste, it's not going to be looking up above in the wrong lines. And so what I mean by that is just type it in, equals negative this divided by that, equals negative this divided by that. It's like being in the Stone Ages again, equals this divided by that. I mean, the first iteration, it would be fine if you anchored it, but for subsequent iterations, did I type it in wrong compared to what it says on the handout here? Oh yeah, you're right. I left out a column. So let me finish this. Thank you for catching that. So I'll move all these over, and I'll call that delta Q. Good catch. Corrected Q divided by the area. That's right. We find the absolute value of the velocity. And you can do it of the, well, don't do it of the corrected Q because you're going to need the directionality of that corrected Q later. So do it for the velocity. So the corrected Q is your original guess plus the change. That's right. Mm-hmm.
Do you also use the most recent friction factor?
Yeah, yeah.
So like, the two that overlap, you use a new friction factor, and all the other ones you use on the second iteration.
Right. That's right. Be sure to switch over to the full Jane equation in subsequent iterations. Don't stick with the fully turbulent. Yeah. So you can just copy and paste the entire block and then make some corrections. You won't have to correct that much though, but it's nice that all the pipe data carries over just with a single big copy paste. So the F values, we want to change that, for example, because we're going to switch over from fully turbulent to the actual Jane equation now. So that'll be one difference. need to adjust. I'm teaching the students in Engineering 111 about relative references. And this is definitely one of those examples where relative references can either save you or kill you. And it's so easy to mess up. So after you do that mass copy-paste, remember, always use the latest value of the flow rate. The indication that things are heading in the right direction is when the percent change is getting smaller. And that percent change is just a reflection of the fact that your delta Q is going to be getting smaller also. You know, once you get all of the pipes below 1% change, then that's good. Now, some of the pipes have very little flow rate, and so those can be a little bit stubborn. And if there's a pipe that's carrying very little flow, I maybe won't be as picky in getting it exactly below 1%. I'd maybe say 2% or something. But in general, 1% is a typical convergence criteria. And then the beautiful thing is once we get our relative references fixed in iteration 2, then we can just literally copy and paste Control C, Control V, and the only thing that we have to change is the iteration number. And you can see that the corrected Q keeps getting smaller, and these percent differences are getting smaller, with the exception of this pipe BC. And the reason why it still has a relatively high percentage is because the flow rate itself on an absolute basis is so low. Compared to all of the other pipes, it has a very low velocity, very low flow rate. And so iterations are cheap. I might as well just keep doing more. In 4 iterations, it's still slightly above 1%, so I can do a fifth with a Control C, a Control V, and just change that number to 5. And then finally, it's down below 1% now. And so here are my final flow rates. Let's see, what column was that in? Column O. Here's my final flow rates. So let's take a look. Sheets later on, but I did want to show you the last part of the example. It asks to find the pressure at each node. Now, we're given one control point, and this is something you're going to need to know for the project. The idea of a control point is really important, and that is that here in our network, we know that something is causing the pressure at A to be 600 kPa. That may be there's a pump there or a reservoir is connected to it, but we're just saying by definition, the pressure at A is 600 kPa. And so from that, what we need to do is find out what's the pressure in other locations as a function of how much loss there is through the pipe. And so these values here for pipe H sub F, we're going to use to calculate the pressure at each of the junctions. And so we can make a list of the junctions. There's A, B, C, D, E, and F. The head at that junction, and then the pressure. All right, so the way that you calculate the head is that A is our control junction. That's the control point where we know it has to be 600 kPa. And so the head there is going to be 600 kPa divided by 9.81 kilonewtons per cubic meter. So that means that there's 61.16 meters of head there. And the pressure is just head times 9.81. Okay, so that one was a little bit circular. But junction B, the flow is going from A towards B, and so the head there is going to be the head at A minus the losses through AB. And here we calculated the losses. That was our last column, the pipe HF. And so now I know the head at B is 57.67, and therefore I know the pressure at B. And here we're simplifying a little bit. We're ignoring the velocity head, which is okay to do for the broad strokes calculations that we're doing here. Okay, so then pipe C, we have to look at our flow direction, and in the context of pipe 1, the flow BC is, where was our final flow rate? Let me do this. So there's my final column O. So BC is negative. That means that the flow is going towards B, and so that the pressure is going to be increasing, although ever so slightly. So it's the pressure at B plus the difference. And this was a very small head difference. so it's not going to have much of an effect. So then the pressure is about the same. The pressure at F, for example. If you look at junction F, we know that the flow is going from A towards F. So then it will be the pressure, the head that we had at A, minus the losses associated with pipe AF. I'm doing it in the wrong spot. Pipe F. So it's A minus the losses through AF. And that gives me the head there, and then the pressure is just based on the head. And so that's the approach that you use. You're looking at the flow directions, your final flow directions. In the end, let me pull up a drawing that shows my final flow directions. Okay, so here are the flow directions at the end. Having a sketch makes it a lot easier to do these head calculations. Oh, that didn't take the arrows with it. But the idea is that in each case, the head is related to the junction next to it. And so, you know, E is going to be lower head than F because the flow is from F towards E. All right. That's it for today. I'll stick around for a few minutes if anybody's interested to try and troubleshoot errors. But let's just look at these announcements one last time. Of the homework, you should be able to solve problem 43. And then these other two problems we're going to get to next time in class. But if you want to get an early start, you can solve your Hardy Cross problem, which is number 43. So I'll see you on Thursday.